All right. Hello and welcome to this episode of Technically Speaking, here in Season 5, Episode 2 with Class 4 Drying and Low Evaporation Materials. My name is Brandon Burton, and I will be your presenter today as we go through this topic. I am the Senior Principal of Industry Relations here at CoreLogic, also the Chair of the ANSI IICRC Standards, and very excited to bring this topic forward today because it really dives into the heart of what I'm most passionate about in the restoration community, and that's the science and the technical behind water damage restoration. It's kind of my core and where I grew up in the industry as a trainer, as an IICRC instructor in applied structural drying and water restoration technician, et cetera. So anytime I get a chance to dive into this side of the industry and get really technical, I get really excited about it. So very excited to bring this topic forward today. A couple quick housekeeping items before we roll into it. First, as we are using Teams here for the presentation, please remember that we use the Q&A for any interaction on questions and answers through the presentation. So find that Q&A tool. It should be somewhere in your Teams menu bar, probably at the top. And at any point in the presentation today, if you've got a question or something that you want to dive into, drop it into that Q&A tool. I won't address it till the end because we do kind of a town hall Q&A session at the very end of the presentation, but log it at any time and we will address those in the order that they are submitted when we get up on the end of the presentation today. And nothing's off limits with the Q&A, by the way. It doesn't have to necessarily be on the topic that we're addressing today. So if you've got a burning question where you got into a debate or an argument at the office around standards or around industry or anything like that, and you want me to sound off from my perspective on any topic related to restoration, feel free to drop that into the Q&A, and we'll do our best to address it. If it's not something I've got a great solution for you here today, it may end up being a topic of a Technically Speaking episode in the future. So with that said, let's roll into it and get started. So today's overview, really simple and straightforward. We're going to go into first understanding what Class 4 is. So I'm going to start with the real basic discussion. Just what is Class 4? Why is it there? Why is it defined in the S500 standard? Talk a little bit about my perspective on the utilization of Class 4 as an industry, et cetera. From there, we'll get a bit deeper into the bones of Class 4 and talk about the heart of what Class 4 is there to articulate around slow evaporation materials and assemblies, and then get into drying considerations related to Class 4. For today, kind of my goal is to start off with a discussion that is specifically centered around the S500 and really identify the key language in the S500 that we should be familiar with as it relates to this topic, and then get into the technical side of what we mean by, kind of the approach for Class 4. So we're going to get real deep into the psychrometric chart today. Another thing that I'm always excited to bring up a psych chart and kind of talk through the science of drying from a psychrometric perspective. I'll talk about this near the end, but we are going to put on a separate episode later on in April that will then dive into the mechanical side of Class 4 and specifically get into equipment installations and specific job scenarios. So we're going to kind of do this in two parts. So today is the theory and the technical, and then we'll get into the practical and the application in April because I've got an episode in between, and I'll talk about that at the end of the presentation today. So first, let's get into what is Class 4. What do we mean by Class 4? There's kind of a history behind this. If you get into older editions of the S500 standard, we used to call these specialty drying situations. In the most recent edition of the S500, that was updated so that we gave it its own designated class as a Class 4 drying scenario. And we gave it a very specific definition. And these were all words that come directly out of the S500 standard. You'll notice anytime I've got the S500 icon in my lower right-hand corner of my screen, what I'm indicating is that I'm citing information directly out of the S500 standard. So paraphrasing, but these are all words directly out of the definition, a Class 4 is a scenario where the moisture that we are targeting, that we're dealing with in the property, is deeply held or bound. And we'll kind of analyze that and kind of talk a little bit about that as we go through this. But in essence, what we're talking about is moisture that's not available at the surface of materials. It's not available in the pores near the surface of the materials. It's not what we would call readily available water or easily accessed water. In addition to this, the definition further articulates that there is significant absorption into low evaporation materials or assemblies. The word significant is really key in this sentence because significant is used in a couple of different ways or a couple different applications in the S500. We also use the word significant when we talk about categories of water and category 2 water, and we mean something very specific when we use that word. Significant in this case means worthy of action. It means that the amount of absorption into low evaporation materials is significant enough that you're going to do something with your approach. Something about the way you approach the drying of that particular property is going to be influenced by the fact that there is moisture that is inside of low evaporation materials or assemblies, and it's deeply held or bound. What you're going to do about it is the third part of the definition. The drying may require special methods. We'll talk a little bit about that. Longer drying times, something very, very critical to note, and substantial vapor pressure differentials, which is the technical side that we're going to unpack very heavily today. That's kind of the theory side that we're going to really expand upon. So kind of jiving into these just a little bit deeper, what do we mean by deeply held or bound water? So this is a little bit redundant in the definition, but what we mean by deeply held or bound water is that the water exists beyond the surface or the surface layers of the material. And typically when we're dealing with a class 4 scenario and we want to validate or verify that we are indeed dealing with a class 4, one of the first things that we need to consider doing is using more than just non-invasive instruments to determine how deeply held the moisture is within that material. Usually we're talking about using some sort of an insulated pin, a slide hammer electrode, invasive measurements to measure materials that are beyond the surface of an assembly to determine if the materials deeper in the assembly are also affected. The second part of that is water that is bound. And by bound, we mean moisture that has chemically bonded with the material. So the sorption has resulted in a state of the water where there is a bond between the water and the material itself. This is something that would be very common in wood, other cellulosic materials as well, and materials that contain certain types of minerals where the water can bond with those minerals in the material, certain types of cement and concrete, etc., which makes the water not only inside the material, but also adds to the complexity of the energy required to free that moisture and drive an evaporation rate. The second part of that definition that we talked about was significant absorption to low evaporation materials or assemblies. We're going to unpack this one quite a bit. We'll get into some of the specific examples that the S500 dictates by materials and assemblies and what directly is being alluded to here. But by significant, again, what I want to stress is that when we identify that the moisture is there, as a restorer, if we determine that that moisture is significant, then the third part of this kicks in. The statement here involves the word may. Drying may require. And I want to take just a real brief detour here and define for you what the word may means in the S500 standard. In the very front of the S500, or any IICRC standard for that matter, there are 5 terms that are coined as important definitions that are defined by the document, that say when you are reading this document, these words carry a very, very specific meaning. And the word may is defined as being permissive. So when a procedure or a practice contains that trigger word may, what the document is saying is that as a standard of care element, we are being permissive that these things can be done by the restorer in order to accomplish the goals that they have set out in water damage restoration. So it is permissive that the restorer use special methods. It is permissive that the job may take longer than typical. It is permissive that substantial vapor pressure differentials be used to drive drying when we find significant absorption in the low evaporation materials and assemblies. So that's kind of a deep dive into the definition of Class 4. Let's unpack now the materials and assemblies a bit further. In terms of materials, low evaporation materials are defined as materials that, due to their porosity, permeance, or internal structure, have a low sorptivity. And what we mean by that is the ability to absorb or transmit water will be slow. So water entering the material, water moving through the material, water exiting the material is going to be slow. Examples of these that are given specifically in the S500 are plaster, wood, concrete, and masonry. These are the 4 very specific examples that are provided for very, very common building materials. So what does that mean from a really simple standpoint? What does that mean? First of all, you're not going to encounter many structures that don't have a significant amount of 2 or more of these materials, right? It's very common in construction of all types that we're going to encounter a decent amount of wood. We're going to encounter a decent amount of concrete. We may encounter, depending on the construction, a decent amount of masonry, a decent amount of plaster. So these are low evaporation materials. And when these materials fit the definition that we covered on the previous slide, significant absorption into these materials, then we may consider them being a Class 4. Secondarily, we also have assemblies. Assemblies are defined as, low evaporation assemblies rather, are defined as assemblies that, due to their construction, exhibit similar qualities to low evaporation materials. The assembly itself, in other words, absorbs or transmits water slowly. Examples of low evaporation assemblies include multi-layer wallboard, multi-layer subfloors, gym floors, and other complex built-up assemblies. The commonality here is multi-layer. The commonality is complexity because the assembly comprises of multiple layers of materials. So we could throw into this firewalls, potentially common walls, shear walls, and other types of construction where multiple layers are typically used to build up the assembly. All right, so that's what we mean by low evaporation materials and assemblies, with some very specific examples of both of these that come directly from the S500 standard. Other language related to Class 4 or these complex drying scenarios that come directly from the S500. I've got 3 sections here I want to cite, and then we'll talk about interpretation and a summary of these once we come out of that. The first section I want to cite is 10.4.3. This comes out of the inspections section of the S500. Drying may require special methods, longer drying times, or a substantial water vapor pressure differential. So this is a recitation of what is in the definitions, in the definition section of the S500 up front. 10.4.3 is calling out that when Class 4 has been determined by the restorer, again, permissive, the word may, special methods, which include longer drying times or substantial water vapor pressure differentials. Section 12.2.2 further discusses Class 4 drying and states that the restorer should, which is another trigger word, and we'll talk about that in a second, develop a drying plan. It is recommended that the components of the drying plan include materials or assemblies requiring individual attention, i.e. Class 4. Let's unpack that statement because that's a really important statement. First of all, the word should in the S500, anytime that you see that word again carries a very specific definition. It's one of the 5 trigger words defined by the document. The word should means that the practice or procedure is a component of the standard of care. All right, a standard of care is also defined by the document as being something that is common among reasonably prudent members of the trade who are trained and qualified and competent in the work. So in other words, anywhere we see the word should in the S500, it needs to happen. That's the way it is done. That's what the standard is defining as the practice or procedure. So in this case, what is the practice or procedure? The practice or procedure is that when we discover or determine Class 4, that we as a restorer should develop a drying plan specific to that class 4 scenario. It is recommended that the components of that drying plan include those materials or assemblies requiring special attention. In other words, if I have class 4 determined, and I've determined that specific materials or assemblies are what constitute that class 4, then I should have a plan specific for how those materials are going to be addressed. Okay. All right. So that's 12.2.2. Further down in 12.5.3, it gets into the plan. Talks about what that plan would look like. Once free water has been evaporated, vapor pressure differential should be increased. Again, there's that word should, e.g., increase the temperature of the wet materials, reduce humidity of the surrounding air, or a combination of both. In addition, it also says that in these circumstances, it can be beneficial to decrease the velocity of airflow. Another statement that I think is going to be really important for us to unpack here today, because it's very commonly misunderstood. So what does this citation state? So first of all, in 12.5.3, which is getting into the discussion of how to deal with these class 4 scenarios, the first and foremost statement is once free water has been evaporated. So these special procedures are intended to deal with the deeply held and bound water, not necessarily the easy water that's available at the surface. And typically, depending upon when the water damage occurred and when we're responding, very commonly we're dealing with a lot of free or surface water initially. And that drying approach is different, right? Drying initially to deal with the easy water will look a lot different than drying when we get into the deeper bound water that is more difficult to address. But once we get to that phase, vapor pressure differential should be increased. So specifically in this citation, it's not permissive. All right, so when we're talking about the vapor pressure differential specifically, it is standard of care. So when we have eliminated the free water, eliminated that surface water, and now we're focused solely on the bound water or the deeply held water, it is standard of care to increase vapor pressure differential, to focus on vapor pressure differential. Now, the example statement, the EG, talks about how that's done, and that's part of the technical that we're going to unpack very, very deeply today. Increasing the temperature of wet materials is one methodology for affecting that vapor pressure differential, or reducing of the humidity in the surrounding air, or a combination of both. It's really important, even though this example statement makes it sound quite simple, it is critical that as restorers, we understand how we impact and affect vapor pressure differential, how we measure it, how we document it, so that we can take credit for it and use it for justification for the equipment decisions that we make. Now, again, the practical equipment decisions, we'll dig into that in our April episode. I'll kind of allude to some of that here at a high level. But what I want to get to today is truly understanding the technical, the science behind what this actually does, how we do it, and why we do it. And then finally, in these circumstances, it can be beneficial to decrease the velocity of airflow. So let's unpack each of these and get a bit deeper into each one of these. But let me just kind of summarize the language that we just looked at. So step number 1 with class 4, evaporate the free water. Step number 2, once we've dealt with the free water, increase the vapor pressure differential. How do we do that? We increase the material temperature where practical. We reduce the humidity of the surrounding air where practical. We also consider, to support this process, the reduction of air velocity, okay, when that will support the process. And again, we'll unpack that. All right, so let's get away from the S500 now, and let's start getting into the scientific principles, the technical principles behind class 4 drying, why vapor pressure is so critical to that discussion, and how we as restorers can kind of take command of that knowledge and put it to practical work. Okay. As I do this, just a quick reminder of the Q&A area within Teams. If at any point you have a question on, especially this, now that we're getting into the technical, but if any point that you have a question, please drop that question into the Q&A tool so that at the end of this presentation, we can start tackling those. And just as a quick shout out, I just wanted to say thank you to Ricky for being the first one to put a question into that Q&A tool. Greatly appreciate you, Ricky. So anybody else who's got a question, please drop it in there. So back to the presentation. So why is vapor pressure important? What is it? How do we control it? How do we evaluate it? How do we quantify it? Those are the questions I want to start unpacking here. The best way to start that approach is, unfortunately, for anybody who doesn't like math, the best way to start that approach is to take a look at a formula. Now, this formula that I have here on screen is an expression. It's the imperial expression of permeance. All right, and permeance is the ability for a vapor to flow through another substance, right? Everything has a different perm rating. Some things have extremely low permeance ratings where the number is really, really low, and we call those vapor barriers or vapor retarders. For example, you may have something like 6 mil polysheeting that has a permeance rating of, like, I think it's somewhere in the neighborhood of 0.02 or something like that. It's extremely low. Then you have things like carpet, right? And carpet may have a permeance rating of 30, right? It's an extremely high perm rating. Well, what does that perm rating mean? To unpack vapor pressure differential, I want to understand what that perm rating means. That rating, at least in an imperial scale, that rating is expressing a number of grains of water that will travel through 1 square foot of the material in a 1-hour period when the vapor pressure differential is exactly 1 inch of mercury. Okay, that's what that number is representing. All right, so for those that have been through a psychrometry lesson, let's unpack that a little bit. Grains, what are grains? Right, when we express grains per pound in the air, like my current temperature is 80 degrees, the relative humidity is 60%. That's a GPP of 91, grains per pound of 91. What does that mean? That means that the water vapor in every pound of air weighs 91 7/1000ths of a pound. A grain is just a unit of weight where 1 grain is a 7/1000th of a pound. All right, so it's very, very quantifiable. So a perm rating, where I have a perm rating, let's say, of carpet, and the perm rating is 30, what does that mean? It means 37/1000ths of a pound of water will travel through every square foot of that carpet per hour, provided the vapor pressure differential is exactly 1 inch of mercury. Now, expressed as a formula, notice how this formula works. All of these factors are multipliers. So if I increase the vapor pressure differential from 1 inch to 2 inch, I'll get twice as many grains through the carpet. Right? If I decrease my vapor pressure differential from 1 inch to a 1/2 inch, I'll get half of the grains of water traveling through the carpet. All right. So in other words, that vapor pressure differential or time or surface area, these are all factors. They're direct factors. And by doubling a factor, we double the results. Okay. So this is why, and the reason I wanted to start with this formula, this is why vapor pressure differential is so important. Because from our context, what we're trying to do is, in this particular scenario that's called out on the slide, I'm trying to drive the movement of moisture through a material and into an air mass where I can then either ventilate that humidity, or I can remove that humidity through dehumidification, to drive that water vapor from one side of a sheet of drywall to the other side of a sheet of drywall. I need to have a vapor pressure differential that is driving that moisture movement. Now, the drywall has a permeance, right? And that permeance, depending on the paint, depending on the type of drywall, etc., that permeance mean less than 1 all the way up to about 2 or 3, depending upon the types of materials and paints and things like that that have been applied. So if I want to affect the movement of that moisture through that drywall, I only have a couple of different choices, right? I can increase the permeance of the drywall. I can put holes in it, right? Or I can manipulate the vapor pressure differential across the drywall. How do I manipulate the vapor pressure differential? I manipulate that through, as the examples told us earlier, making the drywall warmer or reducing the humidity of the surrounding air, right? Sounds really simple and straightforward, but how do I do that? What does that mean? How do we attack that? So that's the piece where now we're going to dive in and start getting super technical. How do we measure vapor pressure, both in air and materials? How do we manipulate the vapor pressure? And if I can manipulate it, that's great, but how do I know if I've manipulated it enough, right? How do I set a goal? If I'm going to set a plan, not only do I need to know that, hey, if I make the material warmer, that will help, but I need to be able to put a number to that, right? And to quantify that and say, I need my material to be specifically this temperature in order to expect a reasonable amount of drying. So I can put that in my plan, set it as a goal, and also use that to communicate why I have deployed particular equipment, deployed that equipment in a particular way, et cetera, to justify the decisions that I'm making and make solid decisions about what needs to be done. So to unpack that, we need to get into the psychrometric chart. Okay, so here's the technical side. So take a comfortable seat. I'm not going to put out a test at the end of this, but hopefully through this process, if you're not 100% comfortable with the psychrometric chart, hopefully this is going to make the chart way more comfortable for you. Because if there's one thing that as an industry I would love to impart on all of us as restorers, is that in order to truly be effective in making drying decisions, we have to understand the relationships that are expressed by a chart. It's a kind of unfortunate from my perspective. It's kind of unfortunate that we have so many tools that automatically do these calculations for us, because if you don't look at a chart and understand how a chart works for psychrometry, that you don't necessarily understand the data that you're looking at, right, and what it truly means. So this will be a great exercise if you haven't looked at a chart in a while. So with that said, let's take a look here. So what is a psychrometric chart? First of all, a psychrometric chart is a chart that expresses the relationship between the thermodynamic properties of moist air, right? The thermodynamic properties of moist air. And the basic relationship is really simple. Along the bottom of the psychrometric chart, highlighted here in my red arrow, are temperatures, right? And you can find this in Celsius or Fahrenheit. The one that we're looking at is in Fahrenheit. And every chart will have a different range, depending on what you're trying to do. Some charts, like the one that we have here, could range from 20 degrees to 120 degrees, which is a pretty common range for a chart you'd want to use in the field for what we do, because you're typically going to be somewhere in that gamut of temperatures. But you can find some charts that have much higher ranges or lower ranges, depending on your application. The second piece of the psychrometric chart that's critical to understand is this top line right underneath the word relative humidity. Here's the key to a psychrometric chart. And if a psychrometric chart has ever confused you, hopefully this is the moment that the light bulb will go off for you. The temperature range along the bottom of the chart and the relative humidity maximum line that I have highlighted in red shows you the thermodynamic relationship. As temperature increases from left to right, the ability for water to be supported as a vapor also increases, right? So at over 20 degrees, the air is really cold. There's not a lot of energy. So it's very difficult to sustain water as a vapor. There's just not enough energy to sustain a lot of water vapor. As you increase the temperature of air, you're literally increasing the kinetic energy of all the molecules that are flying around in the air. That kinetic energy is better at supporting water as a vapor. It can sustain the energy of the water and keep it as a vapor. So the greater the energy content there, the greater the temperature, the greater the movement of all of those molecules, the more water vapor I can support in suspension as a humidity, right? And that's the thermodynamic relationship. It's that simple. This chart is just showing you the relationship between temperature and the ability of that temperature to support water as a vapor. The higher the temperature, the more I can support. So now, understanding that, let's take a look at one specific temperature, 70 degrees. So here we have 70 degrees highlighted on the psychrometric chart. That whole blue line represents 70 degrees. The whole blue line represents 70 degrees on the chart. The bottom of the line represents 70 degrees when it's dry. The top of the line, where I have a red circle, represents 70 degrees when it is saturated, holding as much water vapor as 70 degrees can sustain for any period of time. All right. That saturation point is called 100% relative humidity, right? The bottom of the line would be 0% relative humidity. In between, you see the graduation marks of 10, 20, 30, 40, 50, 60, 70, etc. Now, 70 degrees Fahrenheit at its saturation point, if you draw a line straight to the left, this is how we can extract from that measurements about actual water content in the air. So if we had 70 degrees that was saturated, 100% relative humidity, follow that green line to the left, what we would find is that we have approximately 110 grains per pound of water vapor. So at that temperature, at 100% saturation, the water in every pound of air would weigh 110 7/1000ths of a pound. We'd also find a dew point temperature of 70 degrees. I'm not going to get into dew point today, but in really simple terms, 70-degree air that's 100% saturated is at its dew point temperature because it's saturated. If that didn't make sense, don't let it fry your brain. We'll get into that in a later episode. And then finally, last but not least, the one that we're going to be talking about today, vapor pressure in inches of mercury. At 70 degrees Fahrenheit and 100% relative humidity, the partial pressure of water vapor is 0.75 inches of mercury. That's the pressure being exerted, partial pressure being exerted by the water vapor. That's the driving force that is moving that water vapor to move from one location to another. That's the physical force behind it. All right, so in order to use vapor pressure and vapor pressure differential, we can't just be discussing the vapor pressure of air, right? And typically, we're not trying to dry a building with 70-degree air at 100% humidity either. So the purpose of this first look at the psychrometric chart was just to get an understanding of how the psychrometric chart works. To understand how we use vapor pressure differential, let's take a slightly different dive here. 70 degrees Fahrenheit at a more reasonable indoor humidity of 40%. Where these two lines intersect on the chart, again, we move immediately to the left, and we can determine the vapor pressure of the air at this condition. So if I had a building, and in that building, my air was 70 degrees, and the relative humidity was 40%. The air in that building, the vapor, water vapor, has a partial pressure of 0.29 inches of mercury. That's the force being exerted by that water vapor. If I put anything next to it that has a lower vapor pressure, the water vapor will travel towards that lower vapor pressure. If I put anything next to it that has a higher vapor pressure, then vapor will travel to my air from that source, right? So this will determine the direction of the water vapor's movement. Now, what we're concerned about is a material and the moisture in the material within that drying environment. How do I evaluate the pressure of the vapor in the material? For this, I'm going to plot this in yellow on our psychrometric chart. So let me walk you through a scenario. So let's say in this environment that's 70 degrees and 40% humidity, we have a material that is wet. And I want to understand how well this material is going to dry within this environment. To start the process, the first thing that I want to do is estimate or measure the temperature of the material. How much energy is present in the material? And this can be done a number of different ways. The simplest way to do it is to go grab your protometer MMS, and there's a little button on there that lets you use an IR thermometer. You point it at the material, you press the button, and you take a temperature of the building material using that IR thermometer. If you've got an infrared thermography camera, you can probably use that to do it because it probably has a point temperature measurement. You can use a contact probe for measurement of temperature on a lot of different moisture meters. I know some of the FLIR instruments have IR thermometers on them. A number of the moisture metering kits that are available in the industry today do that. So measure the temperature of the material. Let's say in this case, we find that the material is 60 degrees Fahrenheit. We plot that 60-degree temperature on our psychrometric chart. Now, if the material is wet and there is any free water present in the material, in other words, wet enough that we would call there being liquid water present in the material, then the measurement is really simple. 60 degrees Fahrenheit with liquid water inside the material means saturation. Now, from that point, we move to the left across the psychrometric chart, and we determine the vapor pressure associated with the moisture in that material. The vapor pressure is the temperature of the material, and because there's liquid water, free water, saturation. Take a look at those two vapor pressures, and what we determine is that in the material, water has a pressure of 0.52 inches of mercury. The air I'm using to dry that material has a pressure of 0.29 inches of mercury. The difference between the two is my vapor pressure differential in green on the slide. So the drying force for that material is 0.23 inches of mercury. That's the drying force. Yeah. Now, If you really wanted to be a drying Godzilla, right, you could dive a little bit deeper with this and consider the formula that I shared with you about 15 minutes ago. If the material has a perm rating of 2, right, I'm going to get 23% of that because the perm rating of 2 is based on 1 inch of mercury, and 0.23 is 23% of 1 inch. So if the perm rating is 2 over 1 square foot per hour, right, and I'm going to get about a quarter of that, you're going to get 1/2 of 1 grain for every square foot per hour. That's not a lot, right? That's 1/2 of 1/7,000th of a pound for every square foot for every hour. Over 24 hours, you're going to get 12 grains. Okay. So it's not a lot. So, but this first exercise helps us understand this is how we would measure. If we want to understand whether or not a change that we're making is having a positive impact on vapor pressure differential, this is how we would measure. But consequentially, it's also how we would set a goal. And that's kind of ultimately where I want to drive this to. But first, let's talk about the really, really simple. If I want to make a vapor pressure differential better, then I have 2 choices. The S500 told me that I could make the material warmer, or I can make the surrounding air drier, right? So let's start with the air discussion. Talk about making the surrounding air drier. Before you make any changes to your dehumidification and your humidity control and start bringing in, really, large desiccants or something like that to really go to the extreme, the first thing that you need to do is just ask yourself, the air that I'm using to dry the material, is it in direct contact with the wet evaporating surface? And we've spent entire episodes of Technically Speaking talking about this one point, and it's super, super critical. If you're measuring your temperature and humidity 3 feet away from the surface where drying is happening, that's not the vapor pressure that's doing the work. The vapor pressure that's doing the work is the air directly in contact with the wet surface. And this is part of what gets into the complexity, rather, easy for me to say, in dealing with class 4 drying, is because in many cases, that wet evaporating surface isn't directly in contact with the air inside of a room, right? It's in a cavity, right? Or it's in an interstitial space or an interstitial void, right? That's the air that has the vapor pressure that's directly influencing the material. And that's the air that you need to measure, right? So the thermal hygrometer, chest height in the middle of a room, doesn't tell you what your vapor pressure differentials are. It's the thermal hygrometer measuring the air in direct contact with the evaporating surface. And how you're going to get that hygrometer to that point to make that measurement is going to vary depending on the assembly, but that's the air that needs to be measured. That's the vapor pressure differential that matters. So the first and foremost thing I'm going to share with you is that when you're trying to increase vapor pressure differential, the first thing you want to look at is your air delivery. Are you delivering the driest air to the wet surface? Measure. Determine if you are. If you're only using a thermal hygrometer in one place, and that's chest height in the middle of the room, and you're not using it anywhere else, you're not drying class 4 scenarios effectively, period, right? Because you don't know whether or not that air is being delivered to the wet surface, okay? A good class 4 drying scenario will have multiple uses of a hygrometer, and several of those measurements are going to be measurements at the wet surface. So that's lesson number 1. Now, with that said, if I'm trying to improve vapor pressure differential, then what I'm trying to improve is either the dryness of the air at the surface or something that has to do with the material temperature, and we'll get to that second. Lowering the humidity of the air gives us a really simple and direct result, right? If I take that 70-degree air at 40% relative humidity and I drop that down to 70-degree air at 20% relative humidity, I have a really predictable result. Drier air will give me a lower vapor pressure. In this particular scenario, by dropping the relative humidity down to 20%, what we've done is we've dropped the air's vapor pressure from 0.29 inches down to 0.14. Did that help? Yes. It took our vapor pressure differential from about 0.23 to about 0.38. Right? That's a pretty significant improvement, right? We got about a 50% improvement overall in our vapor pressure differential, which means I should expect about a 50% improvement in drying, right? Because again, these are direct factors. And that's the part of what I really want to drive home with this. If I've improved from 0.23 to 0.38, that's about a 50% change, then we should see about a 50% change in our drying rate, because these mathematical formulas tell us directly that these are all direct factors, right? Now, sometimes this is not practical, right? Sometimes lowering the humidity of the air is not practical, or sometimes lowering the humidity of the air alone isn't going to give me the desired result. So the alternative is, instead of manipulating the air, I may want to manipulate the material. Here's the big, at least the first time that I looked at this, when I was first learning psychrometrics, this was one of the biggest aha moments for me, at least, was realizing the impact of material temperature on vapor pressure. And once I realized this, it completely changed the way that I understood how drying worked. So watch this carefully, because I'm hoping at least it'll have the same impact for you if it hasn't already. Our material is 60 degrees Fahrenheit, right? This S500 says that I can warm the material to increase vapor pressure. Look at what the chart teaches us about how that works. Let's take the material from 60 degrees Fahrenheit up to 85 degrees Fahrenheit. What did that do? And let this kind of sink in for a minute. At 60 degrees Fahrenheit, with free water present, liquid water present, the vapor pressure was just simply taking where 60 degrees, that top of that temperature line, met the saturation curve of the chart, and then go immediately to the left. And we see that our vapor pressure was about 0.52. By raising the temperature of the material to 85 degrees, what we have to realize is that there's still liquid water, right? There's still saturation. So at 85 degrees, it's super simple. Just draw your line all the way up to the saturation line. The new vapor pressure is now about 1.2 or 1.21, somewhere in that neighborhood. Look what just happened to the vapor pressure associated with that water. It more than doubled by raising the temperature to 85 degrees. I didn't have to take the material up to 100 degrees, just bringing it up to, slightly above 80, to a good warm temperature. I've more than doubled the vapor pressure associated with the moisture in that material. Now look what happened to my differential. I went from 0.23 to 0.91. I've tripled the vapor pressure differential, which means I will triple my drying rate. And hopefully that's monumental for you when you look at this. Obviously, the simple answer is sure, a warmer material is going to dry faster. But the drying Godzilla is, by raising the temperature 25 degrees, I will triple the drying rate. That's a much more expert understanding and level of precision for understanding exactly what will transpire because of the changes that you are making associated with warming that material. Now, hold that for a second. Hopefully that was monumental for you. I know the first time that I looked at it, it was monumental for me. Either that or I'm a really strange drawing nerd, one of the two. All right, but hopefully I'm in good company with that. I want to briefly touch on kind of the logistics side of this for just a moment, and also give this to you as a prelude for what I'm going to dive into very deeply in April. When we are dealing with class 4 scenarios, very commonly these built-up assemblies, these multiple layer assemblies, what makes them class 4 is the fact that they create these interstitial cavities and voids, these areas where the wet surface that is drying is inside of an assembly. And we have specialty equipment that is intended specifically to address this. Now, again, just like we talked about a moment ago, the simple answer is, well, yeah, if I've got cavities that are wet, just blow air in there, right? That's going to help dry them. Sure. But if we truly understand the principles that we just discussed, it's not just blowing air in a cavity that's going to make it effective. What's going to make it effective is ensuring that what I'm putting into that cavity is the direct source of the warmest and driest air available within my drying system, to ensure that the materials aren't just receiving airflow, they're receiving energy from that airflow that will raise the temperatures of those materials. I don't need the house to be 85 degrees. I just need that cavity where the water exists to be 85 degrees. and keep the rest of the house at whatever manageable temperature I can to make it easier for my dehumidifiers to work, right? The best possible drying scenarios are those, for your equipment, at least for the technology that we have, are those scenarios that allow for easy dehumidification by keeping the air room temperature while making the materials that I'm drying warmer. By making the whole building 90 degrees, what you're really doing is you're inhibiting the ability for the dehumidifier to make low vapor pressure air. Because the warmer that air is, the harder it is for that dehumidifier to work, right? So that kind of alludes to some of the practical side of what we'll get into in April, is how do I, quote unquote, have my cake and eat it too, right? How do I maximize my ability to create dry air while also maximizing the pressure, the partial pressure of the vapor that is in building materials? And a lot of that comes with these types of equipment that I've highlighted in green down here, these interstitial cavity drying systems that are really the specialty tool for ensuring that the warmest and driest air is put immediately into contact with wet surfaces, while the balance of my drying system is more tuned for dealing with dehumidification and humidity removal. So we'll unpack that in great detail in April. But that gives you some really good, strong hints and things to think about between now and then. The final technical piece that I'm going to dive into here is how do we, on the theory side, how do we use what we've just learned today to set good, effective drying goals? Let's go back to the drying plan conversation here for a minute. And as a part of my drying plan, how do I set my strategy for vapor pressure differentials? Quick reminder, by the way, if you haven't done so already, please make sure that you drop your questions into the chat. And just a quick shout out. Thank you very much, Ricky, William, Samek, and Katie for dropping those questions in there. We're going to get to those in just a moment. If you haven't done so already, drop your questions into the Q&A. So back to the psychrometric chart for a minute. So again, let's say we have a drying environment. In this case, the drying environment is 80 degrees Fahrenheit and 30% relative humidity. Pretty common conditions for the inside of a water damaged structure, right? Pretty common. The vapor pressure associated with that condition is 0.3 inches of mercury. All right, so I know that that's reasonably what I'm going to manage to, maybe based on the geography that I'm at, maybe based on the type of dehumidifiers that I own, my LGRs, for example. I know this is probably about the condition I'm going to manage to. I don't want to be warmer. Maybe it's an occupied building. Maybe there's sensitive building materials. Who knows? I set my indoor temperature and relative humidity targets. So how do I now use that in a class 4 scenario to set my vapor pressure differential targets? The first rule of thumb that I'm going to give you is target a 1 inch of mercury vapor pressure differential. It's a big target, right? Based on the numbers you've already seen us discuss, that's a pretty big target, but set that target. So I want a 1 inch vapor pressure differential. That at least gives me the perm rating for the material, right? So next, take that 1 inch vapor pressure differential and go the opposite direction on the psychrometric chart, go to the left and hit the saturation line. Immediately beneath that saturation line, you will find your target material temperature. If you are going to be drying a building and you know that you're going to be at approximately 80 degrees and 30%, that's your indoor temperature and humidity target, then your material temperature target should be approximately 88 degrees Fahrenheit. That's your material temperature target. Your target is to ensure that the building materials that are class 4, that are built up assemblies, where water the sorptivity is going to be slow because of the nature of the material or the nature of the assembly, that those building materials have a target temperature of 87 degrees. Monitor those building material temperatures, ensure that you're at or near that target. And if they're significantly below that target, that's where your emphasis should be in the specialty equipment installations that we're going to talk a lot more about in April. All right. So that kind of gives you the technical side. I kind of want to wrap this up with a bit of a summary. I'm going to go through a couple quick announcements, and then we're going to transfer over into the Q&A discussion here. I'm seeing some great questions, by the way, dropping into the Q&A. Thank you for that. So first of all, quick summary. So the ANSI IICRC's S500 discusses class 4 as one of the determinations that we will make that relates to how water will evaporate in a building. In particular with class 4, water is deeply held or bound, right? It's difficult for it to move through the material. It's difficult to extract it from the material. I've determined, if I call it a class 4, that there is enough absorption into these low evaporation materials or assemblies that it's going to affect my drying plan. It's significant, worthy of action. My drying plan, therefore, is permissive to deploy specialty methods. It's permissive that the drying times will be longer, and it is permissive that we will manipulate and use substantial vapor pressure differentials to control the drying within that environment. Right? That's kind of the summary of the language that we walked through today that comes out of the S500 and the psychrometric chart. I want to leave you with a challenge with the psychrometric chart, by the way. If today was the first time that you've looked at a psychrometric chart in many months, many moons, maybe even a year or more, I highly encourage that you print up a psychrometric chart, and at least once or twice a week, you play with some of these concepts like the ones we talked about today on the psychrometric chart, because that is the only way that you can visualize the relationship, the thermodynamic relationship that influences how water behaves in an environment. And as a drying Godzilla, right, as a drying technical expert, it's something that we really need to have a mastery of, right? The better we understand how temperature and humidity relate and how that impacts drying and evaporation, the more effective we'll be at making decisions in a drying environment, the more effective we will be at explaining those decisions, documenting those decisions, and ensuring that, you know, various stakeholders, even within our own organization, understand the reason why a drying approach is being taken in a certain way. So highly encourage that a psychrometric chart be an exercise that you walk your brain through at least a couple of times a week. All right. So with all of that said, a couple quick announcements here before we roll into the Q&A. Just as a quick reminder, the Interconnect Beyond All Limits does have a new date. That is March 23rd to 25th in Los Angeles, California. We originally had this scheduled for January of 2025, but because of the catastrophic fires that occurred in the LA area of California, we did reschedule that. You know, the housing and facilities there to support the infrastructure of an event really needed to be used for those that were impacted by the fire event and those that were supporting those victims. So we decided to delay the event until March 23rd to the 25th. So if you haven't already registered, if you have more questions, just scan the QR code that you see on the screen there, and you can go to the Interconnect website and learn more about it, or just go to CoreLogic.com and click on Interconnect, and you can get to it from there. The other quick announcement that I want to make is that next month, we are going to take a deep dive into the new S500 fire standard from a technical perspective. So for those of you that are on the phone with me and you're the water division of your organization, please do me a favor and inform those that deal with the fire side of your organization that they're in store for a wonderful episode next month if they want to join us. And we're going to talk about the technical and practical side of the S700, the new fire standard. So getting into the exact processes and procedures and why specific procedures are so critical and are now required by standard of care. Right? The S700 does for fire what S500 does for water, now that we have that document available and in publication. So join us next month for that. In April, I'm going to dive deep into the specialty drying equipment. So it'll be kind of the second half of what we discussed here today. All right. Thank you very much. Have a wonderful end of your February. Hopefully it's warming up wherever you are, and we will see you next month. Take care.